Given that some nutrients are going to be more limiting than other nutrients, what's the best way to use nutrients when they're limiting? So if there are things that plants can do to allocate nutrients in different ways, what path should they choose? How should they build their tissues? And what processes should get the most limiting nutrients? Well, one rule seems to be, don't use limiting nutrients for secondary purposes. An example of this is plant defenses. There's many ways to defend leaves, and we'll talk about some of these later, but you can have N-containing secondary compounds, such as alkaloids. Alkaloids are a defense that are very effective across a wide range of organisms, but they require N. And when N is limiting, empirically it seems that it's best not to use nitrogen for defensive purposes. Instead, produce other defenses that don't use nitrogen, and use that nitrogen that would have been used for defense for primary productive purposes. So you don't see a lot of limiting resources being used for secondary purposes if other alternatives are possible. Another area that's received a lot of attention is trying to understand the efficiency at which nutrients are used for productive purposes. And the general rule of thumb is that if a resource is limiting, be as efficient as possible with that resource. There are many resource use efficiencies that can be generated for plants. One of those is nutrient use efficiency. And nutrient use efficiency, NUE, and sometimes we'll just say NUE, but NUE is essentially how much production you can have, so something like NPP per unit nitrogen that's going to be taken up or lost. So how much biomass can you produce per given amount of nutrient? This is figure 8.10. It's a synthesis across a wide range of forests that take a look at nutrient use efficiency, which is the amount of biomass per unit N in litter fall. So after resorption of N has already occurred, plants have already taken nitrogen out, and those leaves are primarily dead and they fall to the ground. How much nitrogen is left in that leaf? That ratio of biomass to nitrogen is an index of nitrogen use efficiency. On the x-axis, we have the amount of nitrogen in litter fall, and this is primarily considered to be a gradient of nitrogen supply. So ecosystems that have a lot of nitrogen in them are going to have a lot of nitrogen in litter fall because a lot of nitrogen is cycling, and ecosystems that don't have a lot of nitrogen in them and nitrogen is most limiting are considered to be less productive, and there's not a lot of nitrogen in litter fall. If nitrogen use efficiency was constant, you would get a line that looks something like this. But instead, when we take a look across all of these different types of forests, in T are tropical evergreen forests, D are deciduous forests right there, C are coniferous forests, M are Mediterranean systems, and N are temperate forests dominated by nitrogen fixers. So when you have systems that have a lot of nitrogen in them, for example, as you would find in tropical systems, or those forests that have a lot of nitrogen fixers in them, that the nitrogen concentrations in that litter fall are relatively high. And so the biomass to nitrogen ratio, which is an index of nitrogen use efficiency, is relatively low. They're just not that efficient in using their nitrogen. In contrast, when we get all the way to coniferous forests and some temperate deciduous forests, for example, where they're very strongly nitrogen limited, they don't lose a lot of nitrogen in their litter fall, and their litter has a lot of biomass per unit N. So nutrient use efficiency is really high. So this is a general curve that shows if you start at high nutrient availability and work downwards, that nutrient use efficiency goes up as nitrogen becomes more limiting. The author spent a little bit of time going through some of the determinants of nitrogen use efficiency. And essentially what they go through is a set of calculations to partition nitrogen use efficiency into two components. What they say is that nitrogen use efficiency can be thought of as the product of mean residence time and what's called nitrogen productivity. So if you think about the units for nitrogen use efficiency, it's grams of biomass per gram of nitrogen, and you can partition that into the time that nitrogen is in the system times grams of biomass per gram of N per unit time. So what this is saying is that nitrogen use efficiency can occur because plants hold on to nitrogen for a long time. So if it's nitrogen, we have nitrogen use efficiency. They can hold on to nitrogen for a long time and accumulate carbon as time goes on, or they can be very productive with their nitrogen. So per unit time, produce a lot of biomass per unit N. So nitrogen use efficiency is the product of mean residence time and nitrogen productivity. Here's table 8.6, which shows the nitrogen use efficiency and its components for two different systems. The first one was an evergreen shrub system, and think of this as a place where nitrogen is more limiting, and this is a grass system. So here, when you fertilize an area or it's higher productivity, you tended to go from evergreen shrubs to grass. So in this case, this would be a low nitrogen system, and this would be a high nitrogen system. And I should say that all these examples of nutrient use efficiency here are nitrogen use efficiency, but you can do phosphorus use efficiency just the same. When we take a look at the nitrogen use efficiency of these two systems, for all intents and purposes, we have the same nitrogen use efficiency, but one gets high nitrogen use efficiency by having a high mean residence time, and the other one by having a high nitrogen productivity. So in general, this example shows that there are two ways to generate a high nitrogen use efficiency. Here, grams of biomass per gram of N. One is to have a high mean residence time, and that's what the evergreen shrub does. Another is to have a high nitrogen productivity. So in general, a high nitrogen use efficiency occurs when plants have a high mean residence time. If we take a look at all the partitionings between mean residence time and nitrogen productivity for plants, it's general that the best correlate with something like nutrient use efficiency or nitrogen use efficiency is for having a high mean residence time. Now this part won't end up on an exam, but I'm going to star this a little bit too, because the approach of dichotomizing nitrogen use efficiency into the components of mean residence time and nitrogen productivity have always been a little bit difficult to understand to a certain degree. And part of that is because it's relatively easy to measure nitrogen use efficiency, and it's relatively easy to measure mean residence time. So nitrogen use efficiency is the amount of nitrogen that's in a tissue that's lost from a plant. And mean residence time is generally associated with the longevity of the different tissues. Nitrogen productivity can't actually be measured by itself, and instead we have to determine the ratio of nitrogen use efficiency and mean residence time to get nitrogen productivity. So it's actually really hard to measure nitrogen productivity in and of itself at the whole plant level. And in the end, to understand nutrient use efficiency, you just measure mean residence time, and if it's not mean residence time that's generating high nutrient use efficiency, it's the other factor, nitrogen productivity. So in practice, it's really hard to measure the components of nitrogen use efficiency. And until you can measure both of these, I felt it's pretty hard to say that there's an importance to nitrogen productivity. That's not going to end up on a test or an exam, but as you go through life, and if you have to work with nitrogen use efficiency and you ever get frustrated, this might be part of the reason why. So mean residence time is definitely important, and we know that plants that have a high nutrient use efficiency and are found in places where nutrients are limiting have tissues that live a long time. How do plants achieve a high mean residence time? What can they do to increase how long nitrogen stays in their tissues? Part of that has to do with the way they allocate other resources. And essentially, if you can have high amounts of structure in your tissues or are well defended, those organs are going to live a long time. And the mean residence time of nutrients within those organs is going to be high. So you find that those plants that have a high mean residence time and a high nutrient use efficiency have a lot of structure in them and tend to be well defended. Now we also have to note that it's not just leaves that are important for generating nutrient use efficiency. It's the entire organism. And when we assess nutrient use efficiency, we have to do this at the whole plant level. So that means thinking about leaves, and thinking about stems, but also roots. As you read through the book, you'll see examples that show a lot of the same patterns that we talk about for leaves apply to roots. And I'm not going to go through them here, but you'll read about that. And we have to think about plants at the whole plant level. Lastly, there are consequences to having high nutrient use efficiency for ecosystem dynamics. It doesn't just determine which plants are going to be more abundant, but a lot of the functioning of the entire ecosystem. In short, there are feedbacks to having high nutrient use efficiency that determines other factors also. This diagram shows the components of a plant soil feedback that occurs associated with having differences in nutrient use efficiency. The specific data for this is generated from metrosideros forests on phosphorus-rich and phosphorus-poor soils in Hawaii. What we find and what we're going to do here is just focus in on the phosphorus-poor sites, and then we'll see how that differs between phosphorus-poor and phosphorus-rich sites. Essentially, in phosphorus-poor sites, plants have a long residence time, so high mean residence time for phosphorus, and it's up to 8 years. You can see that phosphorus, once it's acquired, is going to stay within the plant. That high mean residence time generates high nutrient use efficiency. So the amount of phosphorus, amount of biomass that you produce per unit phosphorus is really high. Because it has a high nutrient use efficiency, there are low tissue nitrogen concentrations. And we could probably draw the arrow a couple of different ways, but essentially in these high nutrient use efficiency sites, you get low tissue nutrient concentrations. And you can see that there's relatively low phosphorus concentrations here in the P-poor site. The low tissue nutrient concentrations is associated with low litter nutrient concentrations. So green leaves have low P concentrations, and leaf litter also has low phosphorus concentrations. Once we have low phosphorus concentrations in the litter, that's going to slow decomposition down and return of phosphorus into soil solution. Low phosphorus concentrations, decomposition is slow. There's also a lot of immobilization of phosphorus, such that microbes don't let go of it, and not much phosphorus gets put back into the soil. That reinforces low nutrient availability, which makes nutrient residence times go up even higher, nutrient use efficiency go higher, tissue nutrient concentrations go down, as well as litter. So there's a positive feedback that once nutrient availability starts to decline, for example, there's a set of feedbacks that occur that reinforces low nutrient availability. On the other hand, when nutrient availability is relatively high, there's a positive feedback that tends to maintain high phosphorus availability. So in a rich site, residence time is relatively low, use efficiency is low, P concentrations are high in the leaves as well as in the litter, decomposition speeds up, and a lot more phosphorus is regenerated through microbial processes. So these are just the general feedbacks associated with having differences in nutrient use efficiency. High nutrient use efficiency reinforces low nutrient availability, and having a low nutrient use efficiency is going to reinforce high nutrient availability.